Welcome back to lesson U2A6. This is video number 3 and the last video for the lesson. And here we're going to investigate the intersecting lines in 3D. Remember that two lines may intersect each other or may not intersect at all. If two lines intersect, chances are they intersect at a single point or they intersect at every point, which means that the two lines will be coincident. If two lines do not intersect each other, they're either parallel to each other or they lie on two parallel planes and they're not necessarily parallel to each other. So when two lines lie on parallel planes, but they're not necessarily parallel to each other, we call them skew lines. So let's take a look at some examples. In example 5, we are given the lines L1 and L2, both in vector form. And we have to find if there is a point of intersection. So I'm going to start off with line L1 and write down the x, y, and z coordinates of any point on line L1. The reason why we want to do this is because we want to find out the x, y, and z coordinates from line L1 that can fit into the line L2. So x here would be equal to -3 plus -1s. The y coordinate is 1 plus 1s. And the z coordinate is 4 plus 4s. For line L2, we'll have x equal to 1 plus -6t, so 1 minus 6t. Y coordinate would be 4 plus -t, so 4 minus t. And z coordinate is 6 plus 6t, so z equals 6 plus 6t. So to find a point of intersection means to find the x, y, and z coordinates be the same for both lines. And in order to determine this, then we'll have to find the values of s and t that can make that happen. So we're going to say that since we are looking at two values of x that are the same, it means that -3 minus s must equal 1 minus 6t. It also means that 1 plus s must equal 4 minus t. And it means that 4 plus 4s must equal 6 plus 6t. So to find the coordinates of s and t that will give same x, y, and z coordinates for each line, it's enough that we use any set of equations. So I'm going to choose to use the x and the y coordinates for it. And we'll have -3 minus s equals 1 minus 6t. So the x coordinates must be the same for both lines. So that creates the equation -3 minus s equals 1 minus 6t. Next, I'm going to use the y coordinates, but remember that we can use again any set of coordinates, right? As we said. So we have 1 plus s equals 4 minus t. So we'll simplify each equation. So what we have in here is -3, bring 1 to the left side, so that makes a -4. And bring -s to the other side, make it positive s minus 6t. Second equation, I'm bringing 4 to the left side, 1 minus 4, -3, equals s to the right side, -s minus t. As you can see here, we have the term s with opposite coefficients, 1 and -1, which makes it convenient to solve this system by using the elimination method. And by adding the two equations, we can eliminate the variable s. So 4 plus -3 is -7. S plus -s is 0s. And -60 minus 1t, -7t. So t value must be 1. Therefore, the value of s will be, we can choose either equation. So I'm going to choose equation 1 for it, and we'll have negative 4 equals s minus 6 times 1. Negative 4 plus 6 equals s, which will make the s value equal to positive 2. So with an s value of 2 and t value of 1, so 2 and 1, we are going to go back to each parametric equation for lines L1 and L2 and find the values of the coordinates. So for line L1, we'll have the x-coordinate equal to negative 3 minus s. So negative 3 minus s means negative 3 minus 2. So that would equal negative 5. And the y-coordinate will be 1 plus s, so 1 plus 2, that's a 3. And for the z-coordinate, we'll have 4 plus 4s, which is 4 plus 4 times 2 equal to 12. So therefore, we're going to say that if there is a point of intersection on line L1, it will have to be negative 5, 3, and 12. So let's check and see line L2, how it's doing. For line L2, we're using t equals 1. So we'll have the x-coordinate 1 minus 6 times t. So 6 times 1, that will give negative 5. For y-coordinate, we have 4 minus t, so 4 minus 1, that's 3. And for z-coordinate, we have 6 plus 6t, so 6 times 1, which is 12. So the point of intersection for line L2 has to be at negative 5, 3, and 12. So as you can see, we were able to find the values of s and t that would generate the exact same coordinates for both line L1 and L2, which means that the intersection point exists, and it's made possible when t equals 1 and s equals 2. So the point of intersection is, drum rolls, negative 5, 3, and 12, because it's common to both lines.